Thanks. Thanks. Hey, so I think I will use the mic. We've got some time together. We're going to try to pack a lot in. First of all, thanks to James and Kramer. This is, like they've said, a long time in coming, and I'm really happy to be here. It's been a pleasure the whole weekend. I got to sit in on a workshop yesterday, sat in on Alex's group today, a little critique, and it's been really a pleasure to have this experience and to be able to talk to you guys. And thanks to the friends up in Santa Fe, very generous. So Zahner, kind of what Kramer was alluding to, I don't even know where we fit into this world of contracting, because we really are a unique company. At the end of the day, we're a sheet metal contractor, but the type of projects that we specialize in, which really came about in the last 20, 25 years, when starting with a personal relationship Bill Zahner had with Frank Gehry, really got us down this road on inventive architecture, got us in the forefront of using digital tools, and it all revolves around being able to be part of the design process, then fabricate and install. And we do this to varying extents on different projects. What our approach going in is what's best to serve the project, and that differs depending on the project. We're headquartered in Kansas City, Missouri. Like I said, we've been there. It's 4th generation, going on 120 years. We do have a facility right outside of Dallas where it's mostly production, finishing work. This is our building in Kansas City. We did recently, a couple of years ago, an expansion of the shop floor itself. So this was our way of saying, this is what we do. We designed, engineered, erected this facade, and it's for the shop. It's something we wanted to celebrate because that's really, I think, what sets us apart. We're the ones building it. What is it? Oh, sorry. So Bill Zahner himself, he's written 2 textbooks, really references for the architectural industry. If you haven't seen them, I'd encourage you to look for them. And I was kind of interested too, what's our mix here in terms of students and professionals, practicing architects? Got it all?
About 50-50.
Good, yeah. So this is really a strong reference in terms of thinking about metals as a material, different properties. And we've been building all over the world now, primarily in the States, but more and more we're seeing a demand for this type of work all over. But let's start in New Mexico. This is the project that Kramer was talking about, the so-called turbulence house. Stephen Hall project, he called us up and said, I've got this model, and I want you to scale it up, make that back wall 22 feet, whatever it is, and let's do it. So he sent it to us. We, that's where we start. We had to scan it in, do it a laser scan, and it was an interesting proposition because now it's quite literal. There's glue marks, there's creases, and within the scan, it's at such a high resolution, you actually are seeing that. And there were cases where, just very subtle shifts in the geometry, and now you're in the position of, well, what's really the intent here, and what was just, some guy's finger holding it too tightly. And we had to go through, and a lot of time and energy was spent in kind of rationalizing this model, getting it into a shape that we could build from. And this is, like you're saying, this is 2002, I think. It was still rather primitive in terms of technology. But we had already established this type of construction, which is why we had been working with Stephen anyway, and it's why he approached us with this project. So you can kind of see this, it's a mix of planar surfaces, which are fairly straightforward, essentially stud wall construction. And then these curved surfaces is really where we are using what we call our ZEPPS technology, and we'll see some more examples of that later. But it's our way of slicing this volume up into sections that essentially we're bound by what we can ship, more or less. We work within the geometry and then the constraints of shipping. But this will show you how we think about it in terms of cutting it up and making it into sections and actually fabricating. So it's in the computer model. We can export the data directly to CNC equipment and then assemble it into very accurate geometric forms. That's what you're seeing here. So the other advantage is, we try to push as much of the work into the shop environment as possible. So this is the waterproofing layer that's going on in advance. And then construction. This had its own constraints, I'll say, challenges. But essentially, it's prefab. We were given a slab to work with. And these are self-supporting structural panels. So really minimal equipment for what this was. Everything pieced together, very simple construction. And we're creating really just a shell. It was the fins that defined it. It was, the structural members. And then this was also pre-clad. It's a galvalume, it's called. And I did want to mention before, and I would like there to be a dialogue. If anybody's got a question, raise your hand, shout it out. We're going to try to give a little time at the end as well, but please feel free. If you've got something, let me know. Galvalume skin, which is a little bit unique. It's a very economical material. It's steel. It's like galvanized steel. Instead of an all zinc coating, it's a zinc aluminum. Has a particular small spangle to it. Really quite nice. So, at the crux of what we do, it's all about being part of the design process. This is the introduction of a project that we did in Mexico City. Michel Roquin was the architect for this project. That's him right there. And this is initial meetings in Kansas City. So, we've got the owner here. We've got the contractor here. We've got, it's kind of extraordinary. It's a very fast-track project, large scale, corporate client in Mexico City that was their own GC, which turned out to be a huge advantage. Streamlined all the decision-making process. And these meetings were invaluable. We met maybe 10 times in Kansas City. We met several times in Mexico City. And it was a 9-month process from the day we started design to completion. So essentially, the project, it's more or less a standard shell of a department store. The client was called Liverpool. They're the #2 department store in Mexico. This is a new development that they were co-anchoring with the #1 competitor. So they wanted to really make a statement with this building. That's why they hired this architect. And the way we started to look at it was, and we'll see some more geometry, but it lent itself to just slicing it vertically, having profiled ribs, and then connecting these ribs with horizontals. And this was our way of creating geometry. So we've got a structural system, which we had input on the design, and then everything you see here is within our scope. So that's how we're actually slicing the geometry, creating parts, creating assemblies. In this case, it's Mexico City. We're not installing it. And beyond that, there's not really a precedent for this type of work down there. This is where that strong ownership came into play. They had a precast contractor, did a lot of work with them, and basically, imposed this project on them. So that guy came up to Kansas City several times, lots of mock-ups. But it made us think of it a little bit differently than if we were performing the work. So everything, just for efficiencies, had to be flat packed. There were still 18 semis or truckloads that went down there, but everything individually packed. So now the emphasis becomes, how do you document this? How do you make it as foolproof as possible? And then what's important in the geometry? We're going to see some more examples of this, but I wanted to point out this is the only thing that we actually pre-assembled at our factory in Kansas City. When you look at this overall surface, and we'll see it a little bit later, what became really apparent was anytime geometry came together, any kind of edge, and even generally speaking, that's what we focus on because that's what your eye sees. That's the critical part that has to be right in the field. So we said, okay, anytime there's an edge, we're going to pre-assemble these. We call them shark fins. It's a subassembly with CNC cut pieces assembled into a unit that fits onto a particular spot. And so when we're actually fabricating, let me step back a little. When we're fabricating, everything's done in a model, data is exported, and it becomes essentially a jigsaw puzzle. There's slots in here, corresponding tabs for the connecting parts. We get to the point where we're labeling on each one of these the name of this member. And once you see the geometry, you'll understand that every single one of these pieces is geometrically unique. There's and a very slight degree of dual curvature. So really important, and generally speaking, our approach is we don't try to rationalize the surface more than it has to be. We don't try to dumb it down or make it into consistent units. We don't mind the complexity. Our approach is we'll develop the computer tools, the automation to be able to handle a complex project like this efficiently. Mock-ups are really critical. This is in Kansas City, doing a mock-up of the subassembly itself, a lighting study, which was not in our scope, but an important part of the project itself. So the architect and the lighting designer could come and evaluate how it works with the metal. And I really can't overemphasize the importance of mock-ups. Not just for us in terms of construction, but when you're talking about metals in particular, it's just very, very hard to really get an appreciation of the light characteristics, things that can't really be rendered. So mock-ups are always critical. This is some of the assembly that we were doing, right? So the pink, and for whatever reason, this client, all of their structure is painted pink. It's so here we go with our scope, and we did work with. We worked very closely with the structural engineer on the design of this system. And another kind of general statement I'll make about our approach to building complex geometry, we want to keep the steel as simple as possible. Generally speaking, we're very confident in producing geometric shells ourselves. We've done many iterations of that. We know when we produce the parts, it's exactly per the model, and we've constructed that surface very precisely. The tricky part is getting back to steel. So there's always a lot of different cases, and the approach we came up with here was having these outriggers. It's what anchors the system together. Having those set in the field, and what we identified very early on in this process and communicated to the owner was that you need a very good survey company. That's going to be the critical link that makes all of this work together. And that's another role that we play when we're involved early in the design process. We I said we're confident in the geometries that we're building, so we have to be part of the conversation with the structural engineer on what is the tolerance of the system. We'll design that connection, we'll own that anchor, but there is a limit to, on the structural side, what's allowable. And it's not a straightforward conversation. The types of buildings that we're typically doing don't conform to an AISC tolerance. You can look up in the code and say, I've got 10-story building, I get a 1/4 inch every floor. It simply doesn't apply in most of the projects that we do. So that's a whole step in the process, educating the structural engineer, the steel erector, what the requirements of the system are. And like I said, we shipped everything individually here. A critical part of what made this a success was the installer had a facility about an hour outside. So he would take every other bay he pre-assembled at his facility and could then just hang it in place. So on a typical vertical run, there's 3 individual assemblies that have 4 anchors apiece. And then it's just a matter of infilling with these horizontals. And all of these, like I said, they're all unique parts. They each have a slightly different geometry than the one next to them. Another thing we did on the design side, we said, the way we're going to lay this out is these would be on water lines. They're truly level when they're placed correctly. So it's another check that they can have in the field if something is getting off. And then this is that shark fin that I mentioned, that sub-assembly, sub-assembly that is very precisely defining the edge. And that gets followed all the way across every geometry change. We've got that defined. And more assembly. This is very large scale. And it also lent itself, we picked the middle of the building, said you can work both ways out. We needed to put a lot of people on this at one time. So the solid part that you're seeing is actually just a sheathing layer. So we've established this framework. They're sheathing over it with aluminum, just happen to have a blue plastic coating on it. And then there was a stainless steel skin. So now it's taking shape. You can see all the edges being defined. And this is still not clad in the final skin. It caused an uproar. People just couldn't understand what was going on here. That's the final project. So all of these that you're seeing are actually a stainless steel skin that gets applied over that sheathing layer. And each one of those panels is unique. It has its own number, its own geometry. And again, so that's the strength that, the capability that we have to have internally. How do you automate this process? Getting the geometry is one thing. How do you automate getting 8,000 stainless steel skins out, just the files, and then you have to make them. But that kind of speaks to the type of project that we do, the scale that we're capable of. This turned out to be just an enormous success for the client. This is actually their #1 competitor over there, and they ended up, this whole development is known as the UFO. It's been completely branded, and in fact, Liverpool itself has undergone a rebranding effort using this type of imagery. So a complete success from the client's perspective as well. Yes?
What's the aluminum layer underneath the stainless steel you're doing?
Yeah, good question. This is kind of common construction for us. It's what you're actually fastening into. So instead of, you've got all this framework here. We're not trying to dictate with that panel that you have to go into. Essentially, that's a stud. You could think of it if this were a stud wall. So instead of going into having to find that stud, we're saying give us a sheathing layer, and you can fasten that panel anywhere you want. So it's important too. When we do more conventional construction, we like to specify plywood sheathing. depending on the type of system that we're doing, so that you're not having to find the stud and gives you flexibility on where you're attaching.
So is the stainless, was it black seam, so you did faster?
It was not, and I don't have a close-up of that. It's what we call our inverted seam. So it's kind of a pan. Returns are made inside, so it's a totally flush system and no fasteners, or all concealed fasteners. Very clean. And when you think about it, we're having to pre-make them, with the curve in each one. And probably I don't have it on the scale that you can really appreciate. They were 30 inches wide, each individual panel, 16 gauge stainless, with what we call an angel hair finish. And I think I have some examples later on. Like I said, mock-ups, really critical. This was an early one. It was for a Burberry flagship store in Chicago, which is right here. So what we were mocking up, we own the stainless steel cladding. This was actually a very specialized product. It's got what's called a PVD coating. It's physical vapor deposition. So it's stainless steel. It's very, very highly polished. We sourced this from a vendor in Taiwan that just did a wet honing process to the surface, just made an absolute mirror. And for architects, when you're specifying finishes, number 4 brush, number 6 a lighter, number 8 is considered a mirror finish. This is well beyond that, and there's not a good standard for this. So you have to be very specific about what you want if you want something like this. But so yeah, it's the system itself. We're the shiny stuff here, making the check pattern. This is glass, but it's painted black. It's all opaque. There are no actual window openings on this, except for this corridor here. So the system, we are actually a material supplier to a curtain wall company, and that was important because, it would be redundant if our labor were to go and install this, and we were installing directly to the curtain wall system with the extrusions that they were using, so we designed that connection to work with that.
So is the stainless portion of this floating above the?
It is, yeah. It's proud of the glass, enough to where they could fit in the LED fixtures. So yeah, we had to come up. There's a store in Shanghai that they based this design on, and they actually sent us the assembly that they used for the metal out there. It was very thin, and it was kind of this laminated assembly, and is not something that we do. So we really had to come up with a new system. And when we talk to architects, especially early on, we're really interested in characteristics. What's important? In this case, honestly, reflectivity, but flatness was the overriding concern. So, it was flatness, and then it was accuracy. How crisp can you make that edge? And that's the type of information that we can use that really guides a design. In this case, we went up to a 16 gauge material, and we actually back cut all these edges. We've modified some equipment to where we can actually essentially route out the backside of stainless and fold it over to give a very, very crisp edge. And the other thing too, it's a CNC operation. So we're putting a sheet on essentially a big bridge mill that's got very specialized tooling on it to do this operation. And now what we've done is we've made it completely defined, right? So after all the scoring is done, you can't make it wrong, like dimensionally, extremely, extremely accurate. So it's one of our responses in order to be able to deliver the type of accuracy that this type of project requires.
I'm confused about something.
Yeah.
Is this sort of an applique over opaque glazing, or are those individual panels set within your grid?
This is over the glazing. You know, the individual light of glass is within our grid. We're proud of it, and we extend beyond it.
So you do support the glazing?
We do not. No, it's really the glazing supporting us. So there's a whole extrusion system behind this that's supporting the glazing, and then we're coming off of that same extrusion system. So yeah, just a very high level of integration, and this is another common theme with the type of work that we're doing. On a design level, we have to be very, very integrated with all of the other systems.
How big are the panels out of your shop? And then once on site, how are you able to, do you do a lot of finishing between each panel, the joints in other words? Because it seems, you know, I mean, I understand that we're a distance away from the building in terms of the photograph, but I don't see any lines that show any.
Thank you. Yeah, that's great. Now, in this case, this was where we made some changes to the original design in Shanghai. We actually produced longer pieces, but there's no piece longer than 12 feet. And to give you a sense of scale, this is 16 inches across. But there is a pattern to this, and there are 1/4-inch gaps. And we did have to work there is an expansion joint system throughout this for the curtain wall. And since we're riding on top of the curtain wall system, we have to take in some of those too. So there are certain joints that are slightly larger to accommodate the expansions. But otherwise, I mean, it's a very, and we set it up so in the field, you know, you can put in a precise shim, place your panel, move on. So when you look at this building, that's the quality that you see. It's very consistent gaps that are quite small, and because of the sharpness, you know, it's not a big rounded bend radius on there. It's a very sharp edge, so it gives that level of precision that you don't typically see in sheet metal. Mocking up. So lots of different scale. This is a solid wood piece quite a while ago. It's something we made for actually the Kemper Museum in Kansas City, but we completely fabricated the piece. And this was a sample that we made just to demonstrate the joint, you know, set it to solid wood for review. Ended up, you know, making the entire piece. This is a more recent mock-up in our grounds on Kansas City. It's Peterson Automobile Museum. It's underway. We completed this mock-up, I don't know, a couple months ago for approval to move on to the next stage. This is in LA, gonna buy LACMA. See that one coming. We'll talk briefly about materials. I'm gonna kind of have to speed this up, I think, but stainless steel, really our most popular by volume, very versatile in terms of different polishes and finishes that you can put on. Angel hair is a polish that we developed in-house. It's a random polish, and you know, we've got several CNC machines that are programmed to apply that. So we're now achieving a very high level of consistency with that. A bead blast, so really nice finish. It's literally glass bead that's blasted onto the surface. It's important that you're blasting both sides so you're not warping the material. We did a number of Apple Stores interiors with this material.
Is that an automated process, the glass beading, or do you?
It is. So there's a machine that you're feeding through, but there are many variables, right? So you've got the media itself. There are different sizes of glass bead. You've got the pressure that you're applying it at. You've got the speed that you're moving that sheet through. So, you know, at one point we were offering a lot of different variations on glass bead, and it just got too confusing. So now we've standardized on one process where we can control all those variables. This actually is a Libeskind project in San Francisco, Contemporary Jewish Museum. We use an interference colored stainless steel. It's a specialized process that we don't do. We work very closely with a vendor outside of London to produce this. It's a electrochemical process in which you're growing an oxide layer on top of the surface of stainless, and it's actually, you know, it's light interference. It's a phenomena. There's no pigment. There's no color to this, but you're actually seeing a shift in the wavelength off of the top of that oxide layer and the top of the base metal. So that's why, depending, you know, you can vary the thickness of that layer and get different colors as it is. And this is an example of where we really have to work closely with the design team and understand the intent, because one of the characteristics, one of the properties of this type of finishing is there's a lot of variation. You know, it's not like paint where you can just specify a color. You know, there are only 5 or 6 colors available, and they're general. It's a range. So in this case, we go to London with the design team, with the contractor, with the owner's rep. We make physical samples that define the range that we can work within, and that becomes a standard for the project. Weathering steel, this is more and more, and this is a project not too far from here, relatively speaking. It's a spaceport project, the Foster project. And this, it should be, the roof is not steel, it's a TPO that's colored like that. This is the weathering steel, and there's some other metal around the building. So actually becoming quite popular recently. It's been around for quite a while. Some people call it Core 10, which is not really precise or accurate anymore. Core 10 was a trade name that actually does not exist anymore, but there are particular alloys of steel that have these characteristics of being able to take on an oxide layer and not rust through. So, and again, you know, this is where we really need to be part of the process. Sometimes we see things specified as Core 10 when it's not appropriate. You know, it could be something too thin, or the thing you have to concern yourself with, you know, it's steel, and during this oxide process, there's a lot of staining. So what we do is, oops, it's out of order, but we have a process where we pre-patina this. So we're cycling, we're kind of replicating about 30 years worth of oxide growth on this and getting a very stable surface. More and more we're doing glass. This is a really nice project, and I'll highlight a little bit later on. McCoy Federal Building in Jackson, Mississippi, but we actually did not own the storefront, but all of this glass around here, part of our scope, all of this. Ceramic, anyway, this is a project in Doha, where we used our ZEPPS technology to define these surfaces, and typically where we might put a metal panel on, this had terracotta tile. Oops. Aluminum, this is, oops, sorry. It's the modern in Fort Worth, the Ondo building. So we did this as a really nice, clear anodized aluminum. And at this scale and thickness, you have to be very particular about the alloy. But again, and what goes along with that is this panel system itself. You know, again, flatness was the overriding criteria, so that governs the thickness of the material and the mounting system behind it. Bronze, this is Bowdoin College in Maine. We did a bronze plate that we applied a chemical patina to. Copper as well. This is, again, copper that's been chemically altered, patina applied to it. There it is. couldn't come to Albuquerque without a reference. But it's true. Chemistry is actually very important to this type of process. So this is the weathering steel that we had on the spaceport building. Lots of copper and copper alloys where we are chemically inducing a patina onto it. It's actually something that we've seen. You see these cathedrals with 100-year-old copper roofs, some really nice, rich green patina. And we don't even know really what to tell owners now if you're just going to put copper out in the environment, because the air quality is actually so much better that, that we don't see it changing. There's less sulfur in the air. So this is one way, if you want to induce that look, we can chemically do that. Darkening copper, what we call dirty penny. A zinc patina. We developed it actually for this project for Randall Stout, an architect, had a project in Chattanooga, the Hunter Museum. And there was a whole scope where he wanted to use a local stone at the base, and they just couldn't afford it for the stone itself, and then for the costs that it drove up the structural steel. So we came and said, we'll take a zinc panel and apply a patina to it to simulate the stone. So very successful for this project. He's used the same thing on a couple other projects with us, and we've done different variations on that. There's another project we developed with Randall Stout on zinc to get more of the orange and brown tones out of it. And then we've done different variations on that. For a retail store, did a darkened one. And then even beyond that, this is some mock-up panels that we made for a project coming up in Richmond, Virginia, where we took that Roano Zinc as the basis, but then working with the design team, making some variations on that. And you see some smaller samples that we had made just during the process, communicating with the architect, scaling that up for a mock-up, eventually go on a building. Even more variations, working with Diller, Scafidio, and Renfro on a project at Stanford, McMurtry. So they flew to Roanoke, saw the Stout building, got comfortable with that type of look, but really wanted their own variation. So we did 3 different variations on that. And again, you have to mock this up full scale, a large enough area. And this is one of many mock-ups. We'll end up, they selected this one on the formal mock-up that's being built on the site. We'll actually take some of these panels to simulate, about 6 months of weathering, so you can get a sense for how that weathers. This is something we developed actually with a local artist that we were working with. He was taking stainless steel mesh and just forming it into shapes. And then we took it and actually dipped it in zinc, essentially galvanizing, hot dipping, and then freezing that surface. So, artistically, it offered a lot of possibilities. And then we figured out how to use it. This is actually not far. This is in Las Cruces, right, New Mexico State. We made a series of railings. Malcolm Holtzman was the architect, and did this series of railings where the infill was this frozen mesh material. That gives you a little better view. We actually ended up having to hire that original artist to make these forms. We just couldn't, it's one of these things, again, you can't specify it. It's something that you just have to have an artistic ability for. So occasionally we will bring in artists into our process. We'll talk a little bit about the DeYoung, really important building for us and for the architect. We owned all the copper, but then we really owned much more. Our scope was the entire envelope, with the exception of the skylights. We owned the complete exterior. So again, mock-ups, lots of mock-ups. This was a really interesting process. Herzog and Demeron because they, they're really tactile. They like to play around with materials. So they'd take plastic sheet and heat it up and press different shapes into it just to see, what they liked and how light would respond to it. And they'd send that to us, and then we would simulate that, alter some tooling for the shape. So one of the things I wanted to point out, and this is a very early mock-up, all the variables. So the other thing that we have to interject into this design process is constraints. And in this case, there are a lot of them. And just on this panel, it's copper, but how thick is it? The thickness that you choose really sets the limits to the depth of this bump, which is another variable. And then how many steps are you going to take within this depth? We've got bumps in and out alternating, and then a certain number of steps within that. It's a very strict grid system. People are always amazed at these wild Frank Gehry surfaces that we do, and I tell them, you can be a foot off on the Gehry stuff, and no one's ever going to know. And you cannot be off at all. It's a 400-foot-long facade, and we're wrapping the corner, and that corner has to be between the grid spacing. I mean, there's zero tolerance. It's a pre-manufactured panel. There's no field measuring in this building at all. So, there are panel restrictions, how wide, how thick, how long. It's that has to do with tolerances constraints in our equipment, but then also on a practical level, how are you controlling flatness? How wide is this? The corners themselves. We decided that we had to literally fold that corner in within one panel to get that edge that they were looking at. The fastening system itself, again, no exposed fasteners. So it's a very actually clever system that we used, because the flip side of this is we're installing it. It's got to be efficient to install in the field. And that's another reason why you have to see this through the entire way. And there could be on paper maybe very clever way to fasten, but if it takes twice as long to install in the field, you've killed yourself. It's not even worth doing. So all of these constraints are kind of interwoven too. When you change one, you're impacting others. So it's it's part of the design process. We just have to go through, figure all these out, and then communicate back to the architect. And that's where we really have to find out what's crucial to the design intent.
Which do you prefer, the more precise stuff that you're showing now, or the more
Wow, that's
experience, for example?
That's really hard to answer.
I mean, as an engineer doing the challenges and so forth.
I mean, in one sense, it's almost a luxury with this because it's about precision. And so we can think in those terms and we can quantify everything. We can go through and say, we need X amount of tolerance in this connection because of these variables. So you can follow that through. On the more amorphous stuff, I would say Experience Music Project's the worst example. It's the first time we had done that type of construction, and it got out of control. I mean, since then, we've really learned, like I said, now we're controlling surface geometry very, very tightly. And then the whole trick is, how do you tie it back to the structure? What's your connection tolerance? What's the tolerance of the steel? So that's a different problem, but we've got the surface itself figured out.
So how do you account for movement on that 400-foot long surface?
Yeah, it's a good question. Well, they're all individual panels. So when we think in terms of thermal expansion, say, we're talking about 10 feet. So we have to allow, there's an 1/8 inch gap vertically. There's actually no gap horizontally. But they were happy with the 1/8 inch. And that's all we need within a panel because we're not accumulating tolerance, which is, yeah, there are systems where you would have to account for the entire length. So, that has to be understood kind of up front when you're designing this. What are those movements? There's also a big movement joint horizontal across the middle of this building that we have to play with. And beyond that, this is a base isolated building, the main building. So it's on literally huge rubber bumpers. And it can move 2.5 feet in any direction in a seismic event. The tower is anchored. It doesn't move at all. So there's a moat around that tower where we're having to take up that much movement. So it's got its own detailing issues.
How often are you actually doing the weather wall? I mean, you're usually a skin that's held off the face of the
It all depends. On the DeYoung, we were the waterproofing layer. So, yeah, so there's a stud wall, there's a dense glass sheathing, and then we owned everything outboard. So that was the waterproofing membrane, and then the panel system itself. So the panel system, this is designed to take water out. I mean, it doesn't, we're not, by design, we're not letting water even to the waterproofing layer. It exists, and there's good reason it exists, but that's not the primary barrier.
Do you have freezing problems there in northern?
Not in San Francisco. It's a common issue that we have to design around. Gutters, common case where, depends on the project.
Minneapolis, for example.
I don't know how that's gutted. We've done Gary projects that have internal gutters, where it'd typically be maybe 20-foot welded assembly. So you're dealing with kind of discrete units. If freezing's an issue, heat trace is actually fairly common. So you're not building up ice. We owned all the glass. We owned all the glazing frames on this. We were essentially a little GC out on that job. We had 10 or 12 subs under us. And this was all really design driven. The glass frame itself, it's custom, but it's made of conventional, that's a channel. It's a pipe with a T welded to it. That's a T section. They're all standard shapes. So we had a miscellaneous metals subcontractor making glazing frames, sourcing the glass itself. It was very comprehensive. There's a TPO roof under the copper roof that we owned, the entire envelope. This gives you a little idea. We started out, when you first peel that, it's that nice, bright, salmon-colored copper. In San Francisco, in Golden Gate Park, you get to here in a couple months. I mean, it's a very accelerated growth. And after a couple years, we started seeing a little bit of green forming around the seams. We see it in the tower, particularly. So is the roof. This is a case where we used a design feature. They always had these fingers, is what they call them. They're the raised portions as just a design move for the roof itself. So we used it to put gutters under. And then we had a copper system that inverted seam. So it's a flush system. It's a series of, typically we'd use an aluminum extrusion, but there's a galvanic reaction between copper and aluminum that we wanted to avoid. So actually a roll-formed stainless steel track that we laid in there with clips that would receive the copper panel. And there you go. It's a tower. It's got 30-degree twist. Honestly, one of the biggest benefits we had on this job, we were involved very early, and we have a very strong relationship with a copper producer. So we were able to buy the copper at a very strategic time. It soared after this, after we purchased. I mean, we were scrapping copper for more than we bought it for at the end of this job. Oops. I've talked a little bit about ZEPPS, and it's our approach to defining geometry, essentially. It's the McCoy Federal Building. This was a case where, again, design assist, and it's a federal project for one, so obviously there's some guidelines on single sourcing. And so they went through a whole exercise. Okay, I got steel, I got metal panel, I've got some structure, I've got all this glass. How do I hold up the glass? Lots of different systems, and in addition to that, there's skylights and roofing. So there was an entire effort to bid this out, and it was completely outrageous, like way beyond anything that the budget could sustain. So we came in and said, okay, we'll just own this whole scope, because really it's all interrelated, right? With the exception, we didn't own the structural steel, but we designed it. It got bid out to a steel contractor. But there was just no way to piece this out. Everything's dependent. To do it efficiently, the glass system has to work with the metal system, which has to be supported intelligently. One of the things we do with this ZEPPS approach is try to minimize structure. More often than not, we're taking steel out of a project because we don't want it to define geometry. That's what we're going to do with our system. We build structural panels out of aluminum framing. So we want to minimize structure because it's where you have your largest tolerance anyway. Mock-ups, I can't say it enough. We've got 2 towers now in Kansas City that always have mock-ups on them. In this case, we're mocking up this glass system with this aluminum outrigger. And this is how it's coming together. So we're building, these are the structural units, the ZEPPS as we call them, that has the exact geometry prefabricated in our shop, membrane put on beforehand, and then just simple anchoring connections to a simplified structure. And that's what it looks like. It was really successful project. Like I said, I mean, it was up in the air for quite a while whether or not this could even get built. And it was something that took that design assist effort to realize. This is a fairly recent project in San Francisco, UCSF, and I like to highlight this one because it's a little bit different than what we would typically do. We got a call from the architect, WRNS, the guys that we had worked with on several other jobs, local San Francisco company. They said, we're in a competition. So we're teamed up with the GC. There are 2 other teams we're competing with. Parking garage, 10 floors. We've got a concept for the facade. And if you think about it, I mean, what's a parking garage? You're not going to differentiate yourself with, the angle that you're parking cars in. It's all about the skin. And so they had this concept and a crazy budget constraint. It was literally half of what we had done a garage with them across the street for a couple of years ago. It was $42 a square foot installed in San Francisco, the highest union labor rate there is. And we said yes. It's part of our culture too. We don't like to say no. We want to explore opportunities. And we said yes because we knew we could work with them for one. And they had a very solid concept that we knew had efficiencies that we could exploit. So the concept was, let's take louvered fins across here, put them in different shape, and that's the skin. So it starts out just some hand sketches. How do we unitize this? What are some systems that we can explore? It's all about efficiency. We went through a lot of iterations on the shape of this. So one thing that we identified very early on in the process was the cost driver was going to be that part. And there's so many of them. You know, a lot of times it's not about material. And people can get caught up in materials. And you'd be surprised how little of a portion of a job that can be. But in this case, it dominated. So the on-center spacing became the one critical item on a cost basis. So we established, okay, we can live with 12 inches on center, and it was originally shown at 8. We said we need to bump this out to 12, but let's find a shape that works for us. So we do a lot of extrusion just within our systems, a lot of stuff that's not ever seen, but designing with extrusions, there's a lot of benefits. You can take out process, use of material is very high, little waste. So we've gotten good at designing extrusion. We work very closely with an extruder in Texas. We said, okay, let's work within a 12-inch diameter because there are efficiencies for extruding. I mean, technically speaking, you can go beyond that, but there are implications. So let's work within 12. And let's come up with a shape that, on a design level, you guys are happy with at this 12-inch spacing. And then beyond that, in this case, we were designing in screw bosses into the extrusion itself because that played a very important role in the system itself. Head and sill extrusions, again, custom extrusion, but on any kind of scale, it becomes very economical. Tooling cost, that's probably a $9,000 die to make for the tooling itself. This is probably $3,500, something like this. But those costs are realized very quickly with some of the advantages that you have. So designing this extrusion, coming up with a system now. So we've got the louver, we've got this head extrusion that will fasten into the structure. We own the structure as well. That was all included in that budget. And then the receiving, the upper unit can slide into. So you're only fastening across the top. And again, anything that impacts the field has huge cost implications. So anything you can do to simplify. In this case, we've got an 8-foot wide unit. It takes 5 screws into that tube steel to support it. And it's dead loaded on the top. It's allowed to slip in the pocket on the bottom. We've resolved any of the movement issues seismically. It's really nice. So you got to buy a lot of extrusion. Then you got to buy more extrusion. That was the advantage of this job too. 4,400 pieces of this, but they were all the same, exactly the same. Same shape, same finish, and same length. And we could pay the extruder a little bit more money and have them cut precisely so that we're not even handling it beyond that point. And that's just coming up with the system itself. This is that head extrusion. And we have CNC milling equipment made for extrusion. It's typically what curtain wall contractors would have. But we do a lot of extrusion work. So this is, we've got a mill that can put the holes in at the given angle, dimensionally located. We've got CNC saws that cut this, so we're very confident. This is that processed piece. It's cut to length. It's got the holes in it. And now it's a very simple jig. This is where we're screwing into the screw boss of the louver blade itself. Very simple operation.
So are these louvers fixed?
Fixed, yeah, absolutely. And only 5 different angles. So that was another thing. And it's an interesting point because we gave them the opportunity, even though this is such a low budget. We said, we've got the CNC capability. You can change that angle. So these are the 4 holes that are put in with the CNC mill. If you wanted that to be 1 degree rotated, half degree rotated, you could sweep it across the entire building. We don't care. There's a little bit of cost because exporting the files, that's all automated. We do the computer work, we do the programming within our systems to generate that. So there's very little cost involved with that. You have to, it's now like that would be a particular unit, and maybe it's a one-off out of the 200 on the job. So you have to track it. It's logistics from that point. But that's stuff that you can control, and it doesn't have to be a big cost driver. But the interesting point was that that was not their design intent. We gave them the option to do something more complicated, but it didn't meet their original design. Packaging and crating, shipping is an enormous consideration. And that was the number one decision we had to make on this project was, do we prefabricate? We could have had 20% of the trucks going out if we had just shipped parts and not prefabricated units. And it's a parking garage, which is a luxury. We could have the top deck to ourselves. Usually space is a big constraint. It wasn't in this case. But your labor is quite a bit higher in the field. And you still don't have that same level of control. So again, a mock-up that we had made in Kansas City, shipped to the site, starting to put on the units. There's a starter extrusion that receives that first unit. Handling, always a big consideration, but really nicely resolved in this case. And then you keep stacking them up. So very efficient in the field to do this system. This is the map that we produced. This is actually the one constraint that we imposed on the designer was we said, make these in 8-foot units. So wherever you have this across, our one unit, 8 foot wide, that way we can maximize our shipping. If we went back to the original layout, it was arbitrary, the different lengths. So we said, that's a move that we can make to make us more efficient. So really, really successful project. I mean, it's in a way, and actually this is kind of a trend that we are seeing is some very nice parking garage design. Particularly, we've done a number of projects in San Francisco, and cities now are starting to get involved on a level saying, don't give us a bland, boring garage. We need something more than that.
How do you price this?
Yeah, interesting. We had it told to us. So we had to agree to it. I mean, there was a budget established, and right up front. So this wasn't a case.
Not a cost plus.
Not at all. Fixed. Normally there's a lot of back and forth, and we're making changes and decisions. This was a case where it was established from day one. So if they won the project, then we were on the job for that budget. Normally, that's another function of design assist, where you're working through the budget through the design process. So we'll set it up to where it's a very small design assist contract where we're working directly with the architect developing a design. In that case, maybe you don't even know the material. So there's a lot of variables at play, but the budget's established and we're designing to that.
How do you get it looked like all of the extrusions were just, were the same, but what's the color variation?
Yeah, it's just the angle. So, I mean, they have the exact same finish, but it's just that change of angles. It's a really smart design move. Zera is what we call our process, really developed during the De Young of mapping an image to a pattern. This is a little study that we did outside. This is actually a stairwell at MIT that one of our interns took and put it through our process, made that map. This is a little bit different. It's a project. It's actually a residence in Beverly Hills. And what's interesting about this is this one we said there's kind of a master pattern that was applied to the overall building. And that needed to supersede any panel boundaries. Normally, you're talking about perforations, and you see a margin where the panel returns. And that didn't meet the design intent at all. Yeah, so here, like, this is a panel line right here. And in this case, we're punching through the edges and then mating them up with the corresponding edge. So there's no gap. You can see a line there. And the effect is really nice because now you're just reading pattern. Crazy projects. There's a lot of mirror stainless. This is a canopy where the pattern's wrapping around all three sides. Some signage. This is a facade actually in Kansas City where we're using a couple different things. So we're varying this is the solid portion, if you will. It's just a very sparse perforated grid. We're also applying bumps, actually the same tooling that we used on the De Young, we used on this. And in that way, we're putting, in effect, signage into the facade. This is a student project, Virginia Tech, part of their solar decathlon. And we worked with them. So instead of just perp, we left this tab that could be rotated at a particular dimension to give you a kind of a sweeping effect. So it's...
How are those discs attached?
We're just not cutting through. So we're leaving a little bit of metal, enough so you can give it a twist and it'll stay. So yeah, we're trying to, the next step is to automate this. We're talking to Morphosis right now about a project that they want to use this on. It was student labor, so we had that advantage. And actually, we shipped it flat to them. They bent it in place. Although you can find a video on YouTube where they have a robot with a very sophisticated armature that's bending these. But actually, I talked to a student years later. He's like, oh, no, we bent those all by hand. This is a nice, it's big convention center, Irving, Texas. It's the kind of project that is often not very nice, but we worked with RMJM was the architect, and we had a little design assist to develop patterning. They knew that wanted to be copper. So where they wanted some expression, I don't know if you can get a sense, it's really diaphanous. And there are varying degrees of open area. This is all solid. And they wanted to vary the pattern. So we developed 10 different patterns, in effect, that were placed onto the building. And then they were clever about how it was used. Lots of areas where have two skins, getting a moire effect here. See if this will run. Might take a minute. It's a video here.
You said the two overlaying patterns?
This said, yeah, and you can tell here. So it's a double screen wall. It's probably a foot apart from each other, and you can generate these moire patterns with it. I'm going to skip that. It's going to take too long anyway. Artwork is also an important part of what we do. Typically, it's kind of big-scale art that's kind of beyond an artist's studio's capacity. I've done quite a bit of work with an artist, Jan Hendricks, out of Mexico City. This was a big project that he had in Doha. So it was a courtyard, and this is his model, his plastic model, scale model. And this is very representative of his art. It's very organic, but he wanted that translated into metal. So there's a lengthy process, and it was important to go to his studio and really outline the process. He does things by hand. They get digitized. He actually blows them up to third scale, mounts them on a wall, has a team of artists with Sharpies just filling in, making nice smooth corners. And now it's too big, though, to scan, so he takes a very, very high resolution photographs of the wall and then digitizes that. That gets it to format that we can take, and we have to do some more processing to actually get it to format where we're kiting it. We've got a 10-foot by 20-foot water jet at our facility that we've used for this. This is half-inch aluminum plate. But then it's also designing what you don't see, I don't have really time to get into, but it's the whole hanging system that works with the artwork. And on this type of scale, so this is in Doha being mounted. One panel, is that size. There's two on this elevation. But everything is working together. And then this column in the middle, there's actually two columns, an inner one. Artwork that all works together. This is a more recent project that we did with Jan. He wanted to explore polished materials. Traditionally, he's always worked in painted metal. So he comes to Kansas City periodically. We sit down with him, and we just kind of kick around different ideas. He wanted to do a polished version, basically. He had done spirals before, which is what this shape is. So that was a different process for us. We said, okay, we can't literally, if we were to water jet this, you get that very matte, blasted edge, which doesn't work for this type of construction. So we have a very large milling machine where we can cut these out with a mill, and now we have a really nice machined edge. This is a detail. Beyond that, what we did was hand polish it, and it wasn't really the economical choice, but you can't get this type of handwork radius edge otherwise. We've got a piece in our shop right now of his where we're not doing this. We bought pre-polished material, and we're machining it out and then just kind of easing the edge a little bit. It's a different look, but this was really what he was going after. He wanted it to be like silver jewelry, but on a very big scale. I'm going to go very quickly through a series of slides. Cooper Union, big project in New York that we did. And again, this was all about unitizing. So it's aluminum frame construction. And this is actually a trend that we're seeing more. This is actually a very simple box with a conventional window wall. And then they're using the rain screen to be expressive. So we like that type of construction. So perforated skin. One thing that was determined, this is a common panel actually, where that corner has that same pattern. So in this case, we could save some money by purchasing this. We had to work with a perforator, but it could be done on kind of industrial scale as opposed to us doing it. Our capabilities are more for kind of one-off, and it has to do with the type of equipment that's used to perforate it. But then that panel can be rotated all around and come up with a larger pattern on there. But in the shop, so it's all extrusion work and very complicated connections and geometries where we're actually bending the extrusion and then pre-mounting all the skins so it can be handled as a unit. And again, you can't underestimate this part of the project. I mean, shipping can be an enormous cost. So it also had, these are operable windows. They actually have actuators down there. This is during Hurricane Sandy. A chunk from a water tower came off and got embedded into this screen. But the owner's actually really happy because he's not replacing glass now. He's replacing a screen. Another morphosis project. This is Emerson College in LA. Wrapping up now. This is a rendering model, but really, really interesting project. This is a mock-up of a scrim wall area where, and again, it's, this is actually, it's pretty simple to specify. This is painted aluminum, but, how do you really get that, that feel for how the light is playing off of it, even though it's a conventional metal, when you're shaping it like this? Physical mock-ups, really necessary. Very intensive computer modeling. A couple different systems. These are the big ZEPP panels that we talked about earlier. So that get a cladding on them. And this is that scrim wall. And these are actually just screenshots. We have one of our engineers keeps a log of these, and this is how we're communicating with the field. We're installing it ourselves, but what that means in the union world is we can send 2 guys out, and then we have to hire it locally, which can be really problematic. But so communication is really the key. So we'll make notes, and our field guys are actually quite savvy with not manipulating models, but being able to use models to see things. So we'll point out as part of the design process where we see potential problems. So this is under construction. You see, these are those large, so we were able to stack maybe 3 or 4 of these on a flatbed to send out to. And in the case, the advantage of this type of construction is we had every one of these completed before the structural steel was done. So we can cut a lot of schedule out on a typical project. Scrim wall going up. Really exciting project. It's right in Hollywood. Another morphosis. Never ends. These guys are great to work with, though. Project at Cornell. And again, mock-ups. This is actually kind of neat. This was the original concept for this building. And this is when we get involved. And it was vertical in nature. The overall form didn't change a whole lot, but this was just not something we could resolve. It was primarily a structural issue, how to support these skins. So, with our input, they had to really change the entire concept of this skin. And it moved to a horizontal orientation. And then that opened everything up, because now we're working with glass. We're actually using the mullions to support off of. And it became very economical. The glass guy could install it himself. He's right there. We're prefabricating these individual units, of which there are many, many varieties. But the erection itself, which is always the thing that we're trying to minimize, is very simple. It's 8 bolts into a tab that's already on the mullion, popping out of the seal. So assembly is very quick. I did want to bring up, we also own this soffit area, which in a lot of ways is very gratifying. It was not even a scope we were looking at, but they couldn't find anybody to build this. The scope was awarded to the stud wall contractor, and they just had no idea how to approach it. So we took it, said, okay, you've got your surface. We're going to make a rigid panel out of each one of these. And that way we're controlling geometry. They went into this thinking they could do it like a hung ceiling. And this is a shop drawing. The other advantage we had, in a true plan view, it's an exact grid. So real rectangle. So what that means is, anytime you have curvature, you have to flatten that, and it's some odd shape. But we use it to our advantage, because in fabrication, what that means, we could set up a jig where, in true plan, we know exactly the dimensions. These are offset dimensions for each corner of that jig. All of these parts are CNC cut, tabs and slots. That's the assembly. So you adjust your jig to the dimensions on the sheet, put your parts in, you take 2 cross dimensions, check that it meets those values, and that's it. It gets painted. We had to come up with the whole assembly method, allow for tolerance in the field. But it's, they're 1/4-inch joints. It's really designed at half. If you look at the architectural drawings, and they came back and said, well, We'd really like to see a quarter. At that point, we don't even care. It could be 0. You know, we're butting these things together with a spacer. So there's essentially no tolerance. But we're confident enough in what we're manufacturing that we can achieve this. I'm going to go briefly. We've had an association with Chuck Hoberman, he's the guy that designed this Hoberman sphere, can open in and out. So he's gotten involved in kind of architectural scale, movable facades. So we do the fabricating for him, and we kind of develop systems with him. And he's just done some really remarkable work architecturally. We're still waiting for a project. There's one in the wings that I'll show you, but very inventive stuff. This is built unit at Stony Brook, essentially an art installation. But then we're moving to, this is a project that we're looking at in outside of Riyadh. It was Will Bruder, then when he took off, it's Works Bureau now. But this is the mock-up that we have in Kansas City, it's still in place. These two upper units actually have this movable facade element to them that Hoberman designed, but on a massive scale. It's a huge project, spa project in Saudi Arabia. That's colored titanium is the material that we're using. Yeah, pretty crazy. And then I'm going to bring it back to Kansas City. This is, again, our facility. When I first started working, I started with the company in 1998. This was our first project, Experience Music project with Frank Gehry. And I didn't have an architectural background. I had a 3D modeling background, which is what they needed to do this project. And I thought our advantage at the time was we had 2 of these machines. Silicon Graphics, Octanes, they were $25,000 a piece. And I thought, well, that's the strategic advantage, you know. An architect's not going to buy that equipment, and we can do this. And of course, now hardware is not a barrier at all. You know, you can have a $1,200 laptop and computationally do anything you want. Even software is not a barrier. Everyone's using the same software essentially. So, you know, what I've come to realize is the advantage is, you know, not just our facilities, it's not just the workforce, but it's also kind of this willingness for risk, and which is really what it comes down to, because that's this type of architecture, these type of projects have to have this element of us being willing to do it for this budget without really knowing how we're going to do it. So that's the exciting part from our end. And I'm going to wrap up in just a minute here. I'm going to go through it because what I wanted to kind of get to, some milling that we're doing, panels that we have where we're pressing forms into it, different shading. Here's what we've kind of run into. There's a perception problem, thinking, you know, I can't use Zahner on my project. How do I interact with them? As a designer, how do I come empowered? And so it's kind of an exciting time for us. We're developing and very close to releasing something we're calling shop floor. So in a matter of weeks, you can go to our website, azahner.com. You will see that area. Click on it. And what it is, it's a tool that we're developing. It's really a platform. And the first thing that we're going to release is based on what we did at our own facility. The cloud wall is what we're calling it. But the concept is this is a design tool for everybody that's out there. It's something that you can take a surface and you can manipulate it. You can define the parameters dimensionally. You can define how dense you want these points. You can push and pull them in and out, and then real time, it's developing this system. You're giving it a spacing. We've built the engineering, and we've already done this work on the engineering side, so now we want to push this out. It was really, the mandate was, How do we make what we put on that wall a product? But not a product like catalog product. It's something that can be controlled and manipulated by the design community, but it's a direct interface. So that's what we've developed. Like I said, we're very close to releasing it, and there are many parameters. You know, this cross bracing is actually individually sized per the geometry. You can apply different geometries to it. There are different tools over here, sliders, and this is all happening real time. We've got a back-end modeling that's going on that's actually generating cut files for us. So when you're ready to do it, we already know what we're building. Apply surfaces, different tools that you can use to apply surface to. If you've got an image that you like, that can be the source. So you can pick an image, any digital file, apply that to the surface. Now we're cutting fins into it. So something, don't do this one. Something really exciting. This is, I mean, and that's just up to you guys. You know, you want a logo in your wall, you put it in there. This is what we hope is the disruptive component. You know, we're actually going to tell you exactly what that costs. You know, you're picking materials, you're picking finishes, you're telling us where we're going to ship it. We know everything else that's making it up because it's in the computer and we can pull it out. So real time, you're seeing what it costs. And this has been the barrier and the perception problem that we've had. You know, we have this reputation, especially kind of on the general contractor level where, oh, you're using Zahner, too expensive, move on. So this is our way of trying to be disruptive because we want to give you guys the power. Say, no, I've designed this. This is the price. And the way the system works, you're actually issued a quote, and it's got a very specific product number that you can specify. You can forward that to your contractor or owner, and it's literally the quote. And you can track within the system who's seen it, what they've done with it. So now, you know, we want to empower you guys to really have control. And it's a tool, too. So you can go through and say, you know, you can switch materials, switch, there's going to be some options for the infill panel. And we're going to continuously be rolling things out. But you'll see what impact that has on the material choices. You might, you know, the different spacing, the height. So now it's a tool that you guys can play around with. Eventually, we're going to be rolling out a component for our Zera technology where it's doing mapping on different surfaces, and then a storefront component. Occasionally, we're asked to clad storefronts. I said, well, why not make this a product where we can do some type of specialty metal that goes over your standard anodized aluminum extrusion. And then let's build that into the program, actually make the interface where you're designing the storefront, glass and everything, and we'll deliver that. We're calling it Shop Floor, and it's a matter of weeks. It's going to be up.
Appreciate it, Paul.
Thanks.